Hello and very welcome to this new kind of video series, if I manage. So I am NiceMicro and I've been on a vacation for some time, so that's why you haven't seen some new videos popping up on my channel. So I've been doing these Let's Plays, but in the meantime I really got interested in this machine learning thing, and my vacation I started to dig a little into this thing. So what I am trying to do here is just talk a little about convolutional neural networks, and especially about the convolution part, because that was the part where I had the most trouble. So I was reading books on the internet, I was watching videos on the internet, and I had to really dig through a lot of things to get and implement my own version of the convolutional neural network. So what I was doing, I was trying to understand how the convolutional layer in these convolutional neural networks work, both forward and backward pass. So I can just write my own implementation only using the NumPy. So I did not want to just learn what it does and just trust people who already implemented this already. There are a lot of packages in Python especially where they have pre-programmed everything, and that's really good because that's probably the most efficient way of doing things. People who were coding those probably optimize that code to be very fast. But so convolution, especially the backward propagation, is not that easy to understand. So I was trying to implement my own version of it, the two-dimensional convolution, so I can get a better grasp of it. It's like you don't write your own code for linear algebra, like matrix multiplication and so on, because that's already done and it's very fast and it's not that hard to understand. But for convolution, for me to really understand what's going on, I really try to write my own code. It's not perfectly debugged yet, so I'm not really go deep into the code. I just want to talk about the things about convolution that was really difficult for me. I had really had to go through a lot of sources. So basic convolution, we get two matrices. I figured that the easiest way to demonstrate it is in a popular tabulating software or whatever this called. So let's get our basic, so one of our matrices, this is going to be the input kind of matrix, and then we are going to have, okay, let's just well, it should be 4 by 4. Don't be surprised by the Hungarian language here. So this is going to be our input matrix. We are going to use a very simple convolution operation. And so how do we get the end result here? So in convolution, you can look it up on Wikipedia. It's a very complicated article. So convolution is basically were first developed, maybe, how should I phrase it that way? So first was used for continuous functions in one dimension, but we are usually using the convolutional neural networks for image processing or things like that. And in that case, we have discrete pixels in 2 dimensions. So this is kind of an extended version of that. So how do I convolve this input matrix with this kernel? That should be the question, to get this. So I already set up my matrices. However, I set up this one. It was not good, but anyway, so I already set up you can see that it's gonna be a smaller matrix. So how come? So what we do is gonna get this kernel, which is much smaller. It's usually much smaller than the input. So in the input we are talking about images, so sometimes you're like 200 by 200 pixels, or images can get like really big, and your kernels will be like 5 by 5, 7 by 7, something like that. Usually people in image processing like the odd numbers. Anyways, it's just very simple example. So how do you do it? And this was one of the first things that I really, so that's why I was telling you that I only want to go through those parts that for me was hard to synthesize, and I had to read up a lot of different sources to get this kind of grasp on this. And even though I'm starting with this very basic thing, like what is a convolution, because even what is a convolution is so confusing. So you look up on the internet and people will just get like this kernel has like 2 by 2 matrix, so you get like all these 2 by 2 parts from the input matrix, and basically get the linear combination of these elements with these elements, and you get it here. But it's not that simple. So people will usually just tell you like, this is an A matrix, the input is A, and the kernel is like K or W or something. They'll just like, yeah, A11 times K11 plus A12 times K12. But that's not real. That's not true. That's not convolution. That's called correlation. And convolution, you actually, when you want to convolve this part with this part to get this element, you'll have to multiply this element, so A11 by K22. A11, so let's just do it. A11, what are you doing? So I need to press equals. A11 times K22 plus A12 times K21 plus A21 times K12 plus A22 times K11. So this is basically our convolution operation. You can see like this with this with this with this with that. So basically it's flipped. You can say like if you are doing it and you're trying to implement it in Python or MATLAB or something, you have to flip this matrix. So reverse the direction of both, the axes, like, and then you can kind of do the correlation. So the correlation and the convolution has this difference that in convolution is basically you flip the kernel compared to the correlation. So what do we got here? Yeah, what we got here is yeah, of course, I screwed it up. So I4, so this is that. We have to fix this. I always forget how. What am I doing? No, not this one. Oh my. You can see that it gets confusing. So this is how it works. Yeah, of course. What did I do wrong now? Nothing. Very good. So basically you can see how this works here. So why do you flip the kernel in the convolution? Why is the convolution operation that we use, why isn't it the correlation? So this has a very complicated, so I could find a reason for that, and it's basically convolution, doing this way compared to the correlation has a few mathematical properties that make it better. like more easy to use. It's like, let's just zero everything out here. This is the one actually that I really understood. I didn't really go more deep into this after I saw this, but just do this. There's only one and everything else is 0 in the input matrix. Then you get the convolution kernel in itself. If you're doing correlation, this will be flipped here. You can imagine, because if I flip this, then you could argue that this part would be flipped too. So this is when we are convolving, we are flipping the kernel. Ooh. And if I put that one over in the corner, then of course it's gonna kind of cut off this part. If I put it in the corner here, it will cut off this part. So, you know, yeah, this should be 0, 1. Oh, look at this one, how I done here. So anyways, just fooling around. So this is one of the properties of the convolution that makes it preferable to... Oh, what have I done here? I didn't even realize I can do that. Anyways, just fooling around. So this is why convolution is better in terms of like mathematical... It's better in mathematical terms than the correlation, so that's why we use convolution. So when you want to implement your own convolution, you will have to flip the matrix if you want, you know, if you're implementing it in a certain way, you can go like here, going this direction, like going left to right, and here I'm going right to left. But in general, you will want to implement it in some other way. So anyway, I will talk about that later. So the problem is we usually don't have one matrix and one convolution operation to result in something. Because, like, let's think about image processing. So how do we deal with our images? So basically, our cameras work in the RGB realm, so red, green, and blue components, because this is how our eyes see the colors. So, you know, like, colors are not real. Have you known that? Colors are not real? Yeah, colors are not real, basically. Its light has a continuous spectrum of energy or wavelength, depending on how you describe it, and each light has kind of, you know, a spectrum. Every wavelength has a certain amount, but, you know, your puny human eyes are actually tuned to 3 kind of different wavelengths, and it has like different bandwidth. It's kind of complicated, but basically you can see red, green, and blue colors, and every other color is like, if it's like between the blue and the green, then it will kind of, you know, in your eyes, both the blue and the green receptors will be excited about that light, if the light has a spectrum like that, and it will interpret in your brain as yellow. So that's how we represent it in computers, because computer wants to show the image for you, so it doesn't want to waste all that infinite resources on producing a result that's same as, you know, like the real color of your face. It doesn't matter what the real light looks like when it bounces off your face. The thing is, the computer has to reproduce something that your eyes will interpret the same as it interprets the light that bounces back from your face. But this is not a physics or biology lesson, so let's just deal with the fact that we represent our images as 3 colors, so red, green, and blue. So when we have an image, we have not just a 2-dimensional matrix, it's like a 3-dimensional tensor. When we have, you know, like 3 of these. Okay, I don't want to do 3 of these because it's just too much, but, you know, it can be 3, it can be more. So you can use this kind of method for not just image processing, a lot of things. So for those people who watched any videos on my channel, I played a UFO game. So for example, in the UFO game, you can use like one matrix describes, like, is there a obstacle? Like, there is no obstacle, it's 0. There is an obstacle that's like just up to the soldiers, you know, what waist, that's like 1, and if it's up to the chest, then it's 2, and if it's like an obstacle that covers the whole height of that tile, that obstacle should be 3, and the other should be, you know, the same for the same spatial coordinates, like, is there fire, intensity of smoke there, or you can imagine like what else it could have a lot of different things. So any kind of different data that correspond to the same spatial coordinates but says something else about that spatial coordinate. So in a big picture, in the picture we have the spatial coordinate, and so the one of these matrices tells that each coordinate, what is the green, what is the blue, what is the red, or rather red, green, and blue. Yeah, that is convention. So what do we do? So now we want to produce an output, but we only have one kernel. That's not good. So let's get another kernel for here. And then, how the hell, yeah, I'll just implement it by hand again. So this one is going to be, and now not forgetting the $signs, and then this one will be multiplied by this here. Just follow my lead. So basically I'm doing the same thing I was doing, hopefully, for the first matrix, and just adding these new... No, something is not good here. Oh my gosh, I am so bad at this. So anyways, I'll just multiply this by this, multiply this by this, and add this multiplied by this, and add this multiplied by this. Okay, we got that. Very good. Now I have to fix the coordinates of the kernel, because that's the kernel and that's not moving. Okay, I think I'm good. Yep, I'm good. So this is how we are doing the convolution when we have a three-dimensional tensor. So, okay, so I'm saying three-dimensional tensor, but it's still two-dimensional convolution, because the two-dimensional convolution says that it's 2 spatial dimensions. So you could have 3 spatial dimensions, like I just mentioned the UFO game, so I'm going back to the UFO game. So in the UFO game you have like ground floor, first floor, second floor, and you can imagine a situation when the information surrounding like this block on the second floor, like, I don't know what you want to calculate, but there is like this block on the second floor, and next blocks around them, and the same floor, and the blocks around, and what is second floor, third floor, and blocks above in the first floor. And then you want to like move like the convolution, as the convolution moves through here in 2 dimensions, you want to use that cube moving around in 3 dimensions. And then if the different information for each of these cubes will be in the 4th dimension, which is, but that will be the 3-dimensional convolution. This is 2-dimensional convolution on more than 1 layer. So the 3rd dimension is kind of, you know, like the layers. You are putting layers on top of each other. I guess you understand that, probably. And of course, what if there is not only one thing I want to extract from this feature map? No, this is the feature map. This is, I don't know. This can be a feature map too. I'm confused about the terminology here now. Anyways, so here, this is one output layer, but what if there is more to it. So what can I do is I can have, how do I copy? Yeah, I just used the, anyways, so yeah, it's usually, you know, it's not the, what the hell am I, did just happen here? So escape. So, you know, it's not gonna be the same as like maybe like this, or maybe like, you know, this. And then you want this. Oh, shoot me. Yeah. These are all, the inputs won't change here. Damn you. Oh, yeah. I was not prepared for the treachery of this popular tabulating software. So, okay, so I got this part. And now I have to move my kernel, my convolution kernel to this. Yeah, move, good. And now we can, no formatting, no, no formatting, no. Okay. So now you can see that this second layer of the output is going to be produced, you know, the first one is produced by these kernels, and this kernel uses this input, and this kernel uses this input. This one is produced by these two kernels, so maybe I should just move them a little more apart. And so these are for the second. Damn you. Yeah, these are for, let's use just this one. These are this, so these kernels are used to produce the second layer, and you could have much more. So for even from, you know, like the two input from here, you could get many different outputs with many different kernels. And so your kernel will have 4 dimensions. So the first, you have, of course, x, y, this is x axis and y axis. And then you will have the depth. So this is usually called the depth number. I'm sorry, my native language is not English and the sound is very difficult. So the depth of this convolution will be corresponding to the depth of the input image. So the input image has the 2 spatial dimensions and, you know, the number of layers. So this is the depth, and this will correspond to depth here. And this is the filter number, because the number of these filters we apply, that will make us, that will be what tells us how many output layers will we have. And of course, you could complicate it even a little bit further, which is, you can have not just one image or one input tensor with, you know, the more layers of matrices, but you can have maybe 2 images, which will have, so what will happen is, now we are zooming out. Hopefully everyone watching this can still see what's going on here, so I'm just gonna move this, and I'm gonna, you know, like get a new image. So this is another image. Oops, I shouldn't be writing letters there. Which new image, if I mastered this, oh shit, I'm sorry. I'm copying this, and now, yes, I am pro. So now you have the output also, of course, has multiple images. And what you have to remember, or images, you know, like I'm using the image processing terminology here, but maybe it's not images, maybe it's, just different inputs from the UFO game. It could be from the UFO game, so I don't know. The area around one soldier describes what's around this one soldier. This one describes what's around the other soldier. And you want to do the same convolution operation, so this one will always get the information calculated from the first input of the training set or whatever set you are using, and this one is going to always use the input from here. So I think you can kind of understand what's going on here. And of course, there are two more things to convolution than this, and for that, let's just check out this code here. So you can see here my implementation of the convolutional layer. I was using a class. I am not really perfectly well versed in object-oriented programming, but I found it easier for me, at least, to implement this convolution layer as one class that has all the important variables inside it. So I can just call, like a set kernel, set input, and then convolve, and then calculate the backpropagation, and then update weights. I can just use the variables inside the class. Yeah, you can see that I'm not very well versed in object-oriented programming, but I found it easier than just writing. So on the internet, in some examples, you will have only the functions. So it's not object-oriented; it's just a functional programming, and they will just always pass, the inputs through the parameters, and you can do that. Yeah, for me, this was the way to write the code. You can write it your own way, of course. You should write it the way you understand it better. So, of course, when we initialize our convolution, we make the object from the class. We instantiate. Is that how is it called? Make an instance. Then we are going to do this initializing, and I get all the important things from the initializing to the initialize. So I want to initialize this kernel, output layer, input layer. So this is the depth of the convolution. This is the depth of the input. It's gonna be the output layer number will correspond, the filter, the number of filters, and the kernel size is the size, like in this example, the kernel size is 2 by 2. So in my case, I restricted myself to write, what is this called, the squares. So x and y are always the same. I restricted myself to this because although convolution does not have to be based on squares, it could be based on any kind of rectangles. You have to be rectangles because it's matrices. Anyways, but yeah, I saw that most of the practical cases use square kernels and square input. So yeah, that's what I was going for. So what you are seeing here, you already have how many layers will the input have. You have how many layers the output will have. I set up some default values here. Kernel size. So these are the 4 dimensions of the kernel. 1, 2, and 3, 4 dimensions. And then this is padding and the strides. So when we are doing convolution operation, especially when we are working with images, Sometimes you do not just one convolution operation like this, but then this will serve as the input for the next kernel, and then forever, so on. That's not forever, but you can do like 10, 20, any number you want, but you will have mathematical problems when you have too many layers on each other, but that's not my worry, because I'm just implementing one layer right now. So, but you have to be careful about the things that the output layer is smaller than the input layer, and maybe you don't want that. Maybe sometimes you want that, but the thing is that it's usually practically more desirable to keep the same size for some reason. So you pad with zeros on the sides, which means that oh, if I'm gonna show it to you here, then it will screw up everything, I'm afraid. So let's just how do I copy this? Like this. Okay. So let's get rid of this here for a moment. So I want to keep my things not decreasing. Let's just move things a little. Okay, so I don't want them to decrease, so what I can do is like apply zero padding. And zero padding everywhere. So this is zero padding. It's pad 1. This is called pad 1 because you pad 1 0 in each direction at the end of the matrix. You can do padding 2, then you will have like this, all sides, of course. This is padding 1. And what can you do when you're padding is that, of course, you can, wow, increase, yeah, because now you have all these other numbers and you can do the convolution on the corners. So now we padded one layer of zeros, so padding 1 was used here, and this is a kernel that's a size 2, so we have a bigger output. You know, it would be the same with this one, with this layer, but using. So you can probably understand what I'm saying here. So this is, if you think about it, and you should think about it, if this is a 3x3 kernel, which I could do, but I'm too lazy to write all this, like implement this now in Excel. Oh, I said the name of this program. Anyways, so if I wanted to implement that here, I'd have to write a lot of things, but you would see, as you can see here, if it would be 3x3, and of course from this 4x4 we could only get 1, 2, and 1, 2, so 2x2. The output would be 2x2, but if I pad with 1 zeros on each side, then I can do 1, 2, a 3, a 4. So it's gonna be 4x4 again. And if I have a 5x5 kernel, which would make no actual sense when your input is just 4x4, but if you have a 5x5 kernel, you should pad 2 rows of zeros, so padding 2 for keeping the output layer same size as the input layer. Stride 1 is the next. So what is stride here? So actually, stride is going to cause some confusion in the backpropagation. I'm saying that because it confused me, and I found at least one question on Stack Exchange, which was also confused about this thing, and there was no answer on that question. So I would say that strided convolution confuses people when they are doing back propagation, especially. You can find some materials on the internet, but most people just gloss over that very easily. So, what is strided convolution? So let's get back to here. So what is a strided convolution is, so here this element comes, I should just, sorry, I have to deal with this formatting issue here. Okay, let me delete you here. Yeah, I want to delete you. And I want to get rid of you too by how do I, what? Where is this? Yeah, okay. I got rid of that. Okay, so I can get rid of, no, I cannot get rid of this. Oh my god, no, okay, so this is here, you get your input comes from here, and this bar, your input comes from here, your input comes from here. So probably if you ever took a look at strided convolution, you know what I'm talking about, and if you are interested in convolution, you probably heard about the strides. So the stride is basically, so let's, this element, if stride 1 says, so if I take one step here in the right direction, then I take one step here. If I wanted to do stride 2 convolution, then I get this element. Oh, that was not a good idea. I would get this element from here. Still not working. Damn you. Control C and then Control V and enter. Ah, finally. So I got this element, and then next step, I don't want to take one step, I want to take 2 steps. Yay, then I got a oh my. I got a stride 2 convolution here because I took from here to here, I took 2 steps. Can I actually... no. Software is not as smart as I was expecting. So strided convolutions with stride 2 will go here. So you cannot take another step because that would take, you know, you have to move these 2 steps, 1, 2, and then you are out of the range of your padding. So strided convolution is one way to decrease the output size. Sometimes it makes sense to use strided convolution. Some people say it's not really relevant because you can use another way, a better way to decrease the size regularly of your matrices inside, like between more convolution layers. Like you have an image that has like 200 by 200 pixels, and then you do a few convolutions here and there, like few steps, and then maybe you are like, okay, now I extracted a lot of features from this, and now it's of too many layers, so I want to decrease the layer number. And because instead of the first, you know, like here 2 layers, the depth was 2, and you apply maybe, you know, like 10 or 15 convolution, 15 what is this, convolution layers, filter number, that's gonna be. So filters, every step you apply like maybe 10 filters. First you apply 10 filters, then from this image which has, or from this input which has 2 layers to depth 2, the next step will be depth 10, for example. So, and the next one maybe you want to do like 20, and then you realize that you're making up data from nothing, basically, because, you know, it's like 4 by 4, so it's 16, but you have 2 depth, so that's, you know, 32. And once you had 10 filters and you use the padding, so it will be like always 4 by 4, then it's gonna be 4 by 4 by 10, which is exactly like 5 times more information that you already had in your basic data. So everything is correlated some way or another inside. So people figure that, okay, this is just the data, the amount that this data takes up in the memory is just increasing because you're adding more and more layers, but you don't have additional information. So you cannot just create information from thin air. So basically, if I decrease the resolution, that will still contain sufficient information, still contain the information that is in the original image at the decreased resolution, because you have more layers. And you can decrease the resolution by different methods, not just by striding, but strided convolution is one method that some people use, and I wanted to implement it, and because the backpropagation was kind of confusing for it, I figured I would like to understand how that works. So that's why I added a stride. So here, in the initializing phase, I set out the kernel and how the convolution would work with the padding and the strides. So what I do, m is 0, so we have no images yet because we just initialized the kernel. So this, when I initialize the convolution layer, I just initialize the kernel. I have this m variable for the class that will have how many images I have. X will be the input, but it's I just gave it false. Maybe I should. I'm not sure what would be the good way to do it. I just wanted to, reserve the name, and we don't know exactly, like we don't have the input size yet. This is like a little troubleshooting. So the padding should be 0, so you shouldn't give a negative number. I am not making an integer out of it. I'm gonna use this by myself, so I'm gonna know that I should pass an integer there. But kernel size, I just added it for myself in a way to show what are the meaningful limits for the padding. It's not really a real QA thing where you don't want anyone to be able to pass nonsensical data. I just wanted to, it's for myself for the limits. So padding 0, padding is of course the minimum, and the maximum is kernel size -1. You shouldn't have a padding higher than kernel size -1, because in that case, if you have, like here, my kernel size is just 2, so maximum valid padding is 1. But yeah, kernel size is 2. If kernel size would be 3, we could have padding 2. So if I had padding 2 in kernel size 2, then in the corners, I would be doing convolutions with only zeros, and these zeros are not part of my original data. This is not information from the input. This is thing I made up, and which is zeros, and I don't want to do the convolution on data that is only made up, that has no information in it. Okay, so yeah, that's how I did that. And okay, so stride should be at least 1. It can be infinitely big. And here we did not, just again, we do not have the input, so we don't know how big the input will be. You can have a stride 1 million, and that just will mean that if you have a smaller input than 1 million, then you'll just do the convolution in the top left corner and nothing else. We don't have the y, we don't have the dy, we don't have the size of the output. So this is the output, and this is going to be the for the backpropagation, the derivative of the cost function by the output of this convolutional layer. And of course, I totally did not talk about this. The kernel size here, or kernel initialization. So the kernel, this is what happens first. I should have been talking about that first. Anyways, it just calls this hidden function or private function. Like Python doesn't really have private functions, but anyways, if you know Python more than me, then probably you know how it works. So it's the k self.key, the k self.k, this is gonna be the kernel. It's just gonna get this kernel put into this, and we'll just, you know, filter number from f, depth of that's the number of the inputs layers, and this is ks, just get the shape. So why am I not doing any checks here? Because set kernel is called, so it's private, so technically only the functions inside this class should be calling this, and I want to design this. So I'm always doing the check-in before passing the kernel to this function, of course. So here, the kernel is going to be, it's going to be NP, so it's NumPy zeros with the dimensions of out layer, imp layer, kernel size. So this corresponds to filter number, depth, kernel size. And we have the bias, which is something I have not talked about yet. So bias is basically a vector. It's a one-dimensional thing. It's only the output layer, so it's the filter number. So here, if I wanted to add a bias, it would be here. It would be every layer, every filter, every number. So for all the filters, so here the filter number is 2, so it's 2 numbers. 2 filters would be 1 scalar, the bias. So basically the bias vector will be like a vector of 2. So this one is for this. Let's make it 1. Let's make it -1. And what happens is that after all these things happening here, you will add the bias from here. So this is just one number that you add to everything here. So everything, and this, the other kernel, it will be this, oh my, plus this number, and let's fix this one too, and you can see it. Does it make any sense? Yes, it seems to make sense. Oh no! I screwed up this convolution. This one is still good, so... Okay, let me do it again. Plus this number. So it should be, yep, changing to, like, this should be 335 there. That's good. Okay, now this convolution is good. So now with we convolve with this filter, so depth, and each filter has one scalar, and these scalars add up to be the bias vector. So this is the bias vector. So this is how I initialize my kernel, and then I have some get kernel, get bias, get reshape, something, load from text, set random numbers, set the kernel to something I want to set to, and here I do all the checking on this function before I call the set kernel function. And set input, so when I set the input, it will, from the x 4-dimensional tensor, I get the m, which is the number of inputs, the depth, which is the layers, and the image x, image y, that's the dimensions of the input. So if this depth is not the same as the depth defined for the kernel, then it's not good. Or if it's not a square, I want to work with squares, so if it's not a square, it's not good. Everything else, just the number of images, the size of the input, and the input is set, and that's good. And this is enough. So for the convolution, so here you can do the convolution, and you can set the dy. So when you did the convolution, so you will know what will be the output size. And when you want to do the back propagation, you can set the dy, which is the derivative derivative of the cost function coming back through the back propagation. So this case, m dxy. So the m should be as the same number as the inputs were. The d should be the depth of the output, the derivatives of the output, at least the derivative output there. That should be the same as the filter number here. This should be, these x and y dimensions both should be the same as the y the output was. But here I check that if either the kernel size is 0 or the x is 0, then I shouldn't be doing. So I shouldn't do back propagation if I did not set up the inputs. Well, probably if I did not set up the inputs, then m would be 0 already. So whatever. This is maybe a little too much here. And then just set up dy, and then here's the back propagation that will give you the derivatives of the cost function by the kernel, by the bias, and by x. And then this is just update weights, which will just get how much should you update the weights and the bias, and then some checking, and then okay. So this is basically, this was almost an hour-long introduction into my implementation of the convolution operation, or the convolution layer. In the next video, we will take a little more look into how I actually do the convolution, and I will talk about how to implement it well in NumPy, and I guess that's it for today. So I also guess that's thank you very much for watching this long video, and I hope now you have a little understanding that what I'm doing here, and stay tuned for the next episode where I will talk about how to implement the convolution in NumPy with a little. So it's not the most naive implementation, it will be kind of a little faster one that I found a very good solution on Stack Exchange, so I will show you that one, and then we will do the back propagation. And I'll see you then, I guess. Bye bye!